So now let's try out a couple examples where we're actually finding a total differential. For this first one, I'd like to find the total differential of u. And u is equal to the square root of x squared plus 3y squared. For those who don't recognize it immediately, this would be an example of an elliptic cone. Now, in anticipation of the derivatives that we're going to be doing, we'll refer to this as 1/2 power. I notice that u is a function of two variables, x and y. So setting up our expression for the total differential, I will need two terms, one regarding x and one regarding y. So this will be the partial derivative of u with respect to x times dx plus the partial derivative of u with respect to y times dy. Now to actually evaluate those partial derivatives, we'll do that separately rather than as part of the problem. So partial derivative of u with respect to x, we start with the derivative of the 1/2 power, which will be 1/2 times this quantity raised to the negative 1/2 power times the partial derivative of the inside with respect to x. Derivative of x squared with respect to x will be 2x, and the partial derivative of 3y squared with respect to x will be nothing because y is a constant. So reshaping this into the appropriate form, we can take the 2 and the 1/2 and cancel those out. And then we can take the negative 1/2 power that we see and interpret that as negative means denominator, 1/2 means square root. So square root of x squared plus 3y squared in a radical in the denominator. Now for the partial derivative of u with respect to y, the process will look very similar, with the big difference being what the chain rule gives to us. Chain rule says multiply the derivative of the inside, but the derivative of the inside would be the partial derivative with respect to y. That'll be, in this case, 6y. Meaning that our partial derivative will take the form 3y divided by the square root of x squared plus 3y squared. So same interpretation of this negative 1/2 power that we gave to the previous. So the total differential, du, is going to be equal to partial derivative of u with respect to x times dx plus partial derivative of u with respect to y times dy. So that'll be our final answer for this total differential. Now with that in mind, total differentials are also not limited to just functions of two variables. So I'd like to demonstrate what this would look like for a function of three variables. For this one we have L is equal to x times z times e raised to the negative y squared minus z squared power. So notice that L is a function of three variables this time, which means that to create a total differential I'm going to need three different terms and three different partial derivatives, one with respect to x, one with respect to y, and one with respect to z. The total differential will be dl is equal to the partial derivative of L with respect to x times dx plus the partial derivative of L with respect to y times dy plus the partial derivative of L with respect to z times dz. I would imagine now that you've seen it extended from functions of two variables to functions of three variables, you could probably make the jump to a function of 4 variables or 5 variables, or let's not get too ridiculous. Let's start with the partial derivative of L with respect to x. I have great news in that regard. You have x times a bunch of things that are being treated as constants. The derivative of a constant times x would be just the constant. It's really weird to write this thing with two variables in it and refer to it as the constant. But this is Calc 3. Here we are. For the partial derivative of L with respect to y, this time we're treating x and z as though they are constants, and we'll be differentiating this natural exponential with respect to y. Derivative of e to the is e to the, but then the chain rule says multiply by the partial derivative of that exponent with respect to y. Negative y squared will become negative 2y, and negative z squared will become 0, since x and z are both being treated as constants. We're going to reorder this in a slightly different form, and hopefully one that makes a little bit of logical sense. We're going to put all of the variables first. We're going to put them in alphabetical order, and then we'll put the exponential at the end. Now we've gotten to what I would consider the only real challenging partial derivative for this one, which is the partial of L with respect to z. Taking a look back at the original function, we have two instances of z, one as part of the coefficient of the exponential and one as part of the exponential. As such, we are going to need to make use of the product rule. We'll treat this as the product of xz and e to the negative y squared minus z squared. So this will be first times the derivative of the second plus the second times the derivative of the first. Now, not all of these partial derivatives are, the same level of difficulty. This partial derivative is going to look very similar to the partial derivative in the previous step. Derivative of e to the is still e to the, but the chain rule this time says take the partial derivative with respect to z. Negative y squared will become 0, and negative z squared will become negative 2z. Once again, we're treating x and y as though they are constants. Then for the derivative of a constant times z with respect to z, that'll just be the constant. Now, if you're interested in getting super fancy with this, what you could do is factor out a common factor of our natural exponential as well as an x. If we do factor those out, we'll have x times e to the negative y squared minus z squared times. The first term here, we are going to be left with this z and this minus 2z. Since everything is multiplied, that'll be negative 2z squared. We just factored everything out of this, leaving us with simply a plus 1. We are now ready to write down our expression for the total differential based on what we see above. So dl is going to be equal to this partial derivative, z times e to the negative y squared minus z squared, times dx, plus this partial derivative, negative 2xyz, e to the negative y squared minus z squared, times dy, plus, let's see if we can get it all to fit in this one space here, x e to the negative y squared minus z squared times negative 2z squared plus 1dz, and it all fits. Fantastic. Now if you wanted to, and this is one of my pet peeves, but instead of saying plus negative, you could just change that to a minus, but I don't really feel like rewriting this entire line, so we'll just go ahead and leave it and say that's a good looking final answer. Oh boy. Alright, cool. Made it work.